All right, Giancoli 5.7, satellites and weightlessness. So we put satellites in orbit, and when we do that, we want to make sure they have a tangential velocity, so a speed that's tangent to their orbit. That must be fast enough or high enough so that the satellite does not go back to Earth, but not so high that it escapes the Earth's gravity. So what we're talking about is, here's your orbit, and there's your velocities to stay in that orbit. And you can see as you get farther away, you need to have a little bit greater velocity in kilometers per hour to keep that orbit. But then if you reach a certain amount, right, a certain speed in your orbit, you can escape. So it's kind of like an escape velocity of this orbit. So you want it going fast enough to stay in orbit, but not fast enough to escape the orbit. So what keeps the satellite going is, without gravity, it would go in this direction. That's the tangential speed, right? But then gravity is the force that pulls it in. So that's the centripetal force that keeps this satellite in orbit. Centripetal force is gravity in the case of the satellite. So objects in orbit are said to experience what we call weightlessness. They do have gravitational force acting on them, though. So just because we say weightless does not mean there isn't gravity. All that means is that everything's in free fall, so there's no normal force. That's what weightlessness is. That's when you have no normal force. So, for example, here's 3 different things to look at. So we have a person that they're carrying a package and they're in an elevator. If weight and normal force, the weight on the scale, right, normal force and the force of gravity are equal, that means that our acceleration is 0 and we're moving at a constant speed. Here, you see that our weight, right, on the scale is more than the force of gravity. It's because we're accelerating upwards, which means this force, the normal force on our scale, is greater than the actual weight. So your weight will be greater than what it actually is when you accelerate upward on a scale, and you can see it's 1/2 g. That's pretty darn fast. Now let's say the cable on the elevator breaks. When that happens, and there's no force going up, and the only thing that happens is gravity, then we're in what's free fall or weightlessness, where acceleration is just g, 9.8, which means our weight on the scale is going to read nothing because there is no normal force, because there's nothing holding us in place. We're just falling. So when we're just falling, that's what weightlessness is. That's when gravity is the only thing acting on you. Very similar to free fall. So more properly, this effect is called apparent weightlessness because the gravitational force still exists. And it's experienced on Earth as well, but only briefly. And here are some examples. Ice skater jumping, a ballerina jumping, a skier jumping. But anytime we're in the air and the only thing acting on us is gravity, that is this weightlessness that we feel. Because gravity is all that exists. Even if the air resistance is there, it's minimal, not important. So here's an example of a problem. A geosynchronous satellite is one that stays above the same point on the Earth, which is possible only if it is above a point on the equator. Why? Because the center of a satellite orbit is always at the center of the Earth. So it is not possible to have a satellite orbiting above a fixed point on the Earth at any latitude other than 0 degrees. So geosynchronous satellites are commonly used for TV and radio transmission, weather forecasting, and as communication relays. So determine A, the height above the Earth's surface such a satellite must orbit, and B, what's its speed? And we're going to compare to the speed of a satellite orbiting 200 kilometers above the Earth's surface. Kind of encompasses a lot of different types of problems, but we're going to do it all in one. Do it now. All right, so here is our problem. We got Earth satellites a certain distance above the Earth, makes one rotation in 24 hours. So we have a time period of 24 hours to make this happen. Knowing that, we know the force of gravity is the constant times the mass of our satellite times the mass of the Earth divided by r squared, which is going to be the distance from the center of the Earth to the satellite. R is the radius of the Earth plus whatever d is, that distance above the Earth's surface. Okay? So we know that the force of gravity is our net force, so that's going to be equal to ma, which is the mass of the satellite, v squared over r. And now we're going to start doing some work with v. we know the velocity of our satellite, okay, is 2 pi r over t, which is our time period, which is 24 hours. So if I substitute this in for v, okay, and square it, here's what I got. So I got, well, let's do this first. Mass of the satellite cancels out. So I got big G, mass of the Earth over r squared, is equal to, and I'm going to square this, so 4 pi squared r squared over t squared over r. This r cancels here, and here's what I got. And again, I'm trying to solve for r. I can cross multiply this, right? R squared, so 4 pi squared r squared is equal to g mass of the Earth times t squared. And these r's, well, these r's multiply, so it's r cubed, sorry, r cubed. Then I divide by 4 pi squared. And then I got r cubed equal to this, and I can solve for r, the mass, with doing my t, which is 24 hours. 24 hours in seconds is 86,400 seconds. If you need to see the conversion, just Google and you can find it. Mass of the Earth, as we've been using, is 5.98 times 10 to the 24th kilograms. So I know the constant, and I know pi. I can solve for r cubed, right? And just take the cubed root of your answer. So you punch all that in, take the cubed root, and r is going to equal 7.54 times 10 to the 22nd. And that should be cubic meters. Yep, that's what I got, cubic meters. Okay. So that's my r cubed, sorry. And then I take the cubed root, and then r will be equal to 4.22 times 10 to the 7th meters. And that's going to be my actual radius. So that's going to be this total distance, right? So if I take this number minus that will tell me the distance above. So I subtract, and my calculator, I didn't do this one on paper. So if I take 4.22 E7 minus 6380123, I get about 3,035,000. Try that again. 4.22 E7 minus 6380123. There we go. 35 million meters above the surface of the Earth. And that's how far above the surface of the Earth I'd have to be to have that satellite do what I want it to do. So now, let's say we want to find the, and then B says, what's the satellite speed? Well, we said velocity is 2 pi r over t. So if I wanted to find the velocity, I could use that equation, right? So v is equal to 2 pi times my r, which is this number, right? Because that's going to include everything. 4.22 times 10 to the 7th over my 86,400 seconds. And when I do all that, I get just a shade over 3,000 meters per second. So that's how fast my satellite's going. So that's going to be the tangential velocity of my satellite. It's going to be 3,070 meters per second. And then C says, compare the speed of a satellite orbiting 200 kilometers above Earth's surface. So it's going to be a little bit closer. If I want to compare that, a essentially I would just change my radius, right? And I would say, okay, so it's 200 kilometers, so if I go 6380123 plus, and then 200 kilometers in meters would be 200, right? 200, is it 200? 200, sorry, 200, and then add 3 zeros. So it'd be 200,000 meters, add that, and I get, for my R, I change that to 658 with 4 zeros. That goes into there, and now I solve for my new velocity, which would be 2 pi times 6580123 divided by 8640. And I were to get about 7,000 meters